Have to see how this goes. Okay. For the 75th attempt on this material, section 5.4. This is what you've been waiting for. And we're just doing more integrals. In fact, specifically, we're going to do net change theorem. Notation for antiderivatives, or otherwise known as indefinite integrals. Aren't you glad I can speak today? Another name for antiderivative of a function f is the indefinite integral, and is denoted by the integral of f of x dx. Notice there's no limits on there. So the indefinite integral of f of x with respect to x is capital F of x. Don't forget your plus c, where if you were to take the derivative of your answer, that gives you the integrand. So let's take a look at a few examples, and keep in mind I would use your table of indefinite integrals. They've got one in your book. You can also Google it. You can also just have your derivatives memorized, and that will work as well. All right, so let's go ahead and take the integral of these next few examples. Now, you could take the integral one term at a time, and you could write it out like that, or take the integral of each one. All right, so the 3 here is going to go along for the ride. The integral of e to the t is e to the t. The integral of the secant squared of t is the tangent of t. Remember, we take the derivative of the tangent to get a secant. And then don't forget your plus c. For the next example, I'm going to do the exact same thing. I'm going to take the integral of each individual term here. And you can take this step to write them all out, or you can just do them individually. We have more tricks up our sleeve later. But again, remember, you're looking at these and trying to figure out what the derivative of what gives me this expression. Except for this one's power rule. So you increase the power by 1 and then divide by that power. Here, you are doing the natural log of the absolute value of x. And here, 1 over x squared plus 1, that's the inverse tangent of x. And then don't forget your plus c. And again, don't forget, if you don't remember what these things are, got to have those derivatives memorized. All right, next we're going to evaluate this integral. Now, right now, with this integral here, we can't take it until we distribute out the x. So I'm going to have, this is x to the 1/3, and this is x to the 1, so this will be x to the 4/3. And then this is x to the 1 and x to the 1/4, so those will be x to the 5/4. Now I'm going to take the integral. So I'm going to add 1 to this. So I'm going to add 3/3 to 4/3. So I've got 4/3. I'm going to add 1 to it. And then I'm going to divide by that power. And same thing here, x to the 5/4. I'm going to add 1 to it. And then I'm going to divide by that power. And then this one has limits of integration. It's as x goes from 0 to 1. So I'm going to have to simplify and evaluate. So remember, when I divide by a fraction, I'm going to multiply by the reciprocal. And I'm going to evaluate this from 0 to 1. So evaluating this for 1 first, I'm going to have 3/7 plus 4/9 minus 0, and that's going to give me 55/63. For the next one, I'm going to take the integral of each piece. So the 2 goes along for the ride. Take the antiderivative of the e to the x is going to be e to the x. Next, the 4 is going to go along for the ride. Now the integral of cosine is the positive sign. And then I'm going to evaluate this from 0 to 5. So I'm going to plug in the 5 first. 2e to the 5 plus 4 times sine of 5. And I'm going to subtract from it, plugging in the 0. So 2e to the 0 plus 4 sine of 0. And I'm going to end up with 2e to the 5 plus 4 sine of 5. Just leave these values as they are. And then this is going to be 2, and then this is going to be 0. So I'm going to have minus 2 minus 0, but I don't need to write minus 0 in there. Okay, application of the FTOC, the fundamental theorem of calculus. Basically, you take the integral and you do the upper limit and you subtract from it the bottom limit. And this is always true as long as your antiderivative is the derivative of your integrand. Okay, and we call this the net change theorem. You've seen this before. We've been talking about this already. This book just likes to describe things a bunch. Okay, so for example, let's just kind of look at where you've got a story problem. Suppose R is the rate at which the heart is pumping blood in liters per second, and T is the time in seconds. So just imagine we've got this function here, and we've got liters per second for our output. And then we've got seconds for our input. And here's some function. They're saying, what is the units? What are the units of this integral? R of t dt from 0 to 10. So just imagine here you're going from 0 to 10. Okay, so if you were to have little rectangles in here for area, right? What would the units of these areas be? Okay, what would the units of these areas be? Well, let's take a look. The height would be liters per second. The width would be second. So if I do height times width, I'm just going to end up with the liters. So the meaning of the definite integral of 0 to 10 of r of t dt would be the net change of liters pumped from t equals 0 to t equals 10 seconds. All right, let's look at the next one. The velocity function. Velocity function is given by t squared minus t minus 6 in meters per second. So let's graph this velocity function first. I've got this point right here. Let's see, 1, 2, 3, 4 here. 5, 6 there. Okay, and then we're getting to some symmetry. Oh, too far over. There we go. I was doing something like this. All right, there's the graph of our velocity function. Now, for the next problem, they want us to find the displacement of the particle. All right, so the displacement of the particle is just the integral of the velocity function from 1 to 4, from the time period given, okay? So this displacement, remember what displacement is. That's if I get in my car and I get out of my car and I walk, right? So I go walking, I walk a path and then I come back and then I get back to my car. Displacement would say that if I look at where I am at the end of that trip, displacement would be 0 because I started at my car and I ended at my car. Total distance, okay, total distance is going to be different. So displacement for this first one here, I'm writing the wrong thing. So displacement for this first one here is just doing the integral as is. Okay, so I'm going to end up with t cubed over 3 minus t squared over 2 minus 6t, and we're doing that from 1 to 4. So that's going to give us, here we go, 4 cubed over 3. So 4 cubed over 3 minus 16 over 2 minus 6 times t, which is 4. And this one in here, going to give me negative 32 thirds. Minus, I'm going to do it for the 1. I'm going to have 1/3 minus 1/2 minus 6. So 1/3 minus 1/2 minus 6. And this is going to give me negative 9/2. All right, so that's his displacement. So from the time period of 1 to 4, and this is in meters, it means I'm going to be negative 4.5 meters to the left of my starting point. All right, now distance traveled during this time period. So we're going from 1 to 4, and I'm going to just take another peek. Here is so just kind of imagine, here's the velocity function. Here's 1. Here's 4. If I want to find the total distance, what I need to do is I need to take the negative of the area underneath the curve, because a minus minus will make it plus. That'll make it so that I'm counting that value. So I need to do the integral from 1 to 3, take the negative of it, so that makes this thing positive, so that it'll count. Can't make a smiley face. I'll do it up here, I guess. Forget you, smiley face. So I've got to do that of my velocity function. And then I'm going to add to that from 3 to 4 this positive piece of the velocity function. Okay, so the integral of the velocity function we did over here. Okay, so I'm just going to rewrite that. So I'm going to have, the first one, remember, is negative, so I'm going to distribute that negative out. Negative t cubed over 3 plus t squared over 2 plus 6 times t, and that's going to go from 1 to 3. And I'm going to add to that the regular integral, t cubed over 3 minus t squared over 2 minus 6t, and we're doing that from 3 to 4. All right, so what we need to do is plug all those in. So for this one here, we're going to plug in the 3 first, and then we're going to plug in the 1. Don't forget to subtract them. 1/2 plus 6, and then here's this is the plus, and then we're going to do it for 4. So actually we did 4 earlier. We know that that was negative 32 halves, thirds, lies, thirds. And then we're going to subtract from it. All right, and after much deliberation, you end up with 61 over 6, or just 10.17 meters. And that's your total distance. And I had to sniff. All right. I hope that was worth the wait. I'm sorry I'm having so many issues here at the end. Borrowed another friend of mine's computer, and it's basically the exact same thing. So thank God for that. All right, just take it slow and steady, and keep your wits about you. Again, if you're having a hard time with integrals, make sure you have your derivatives memorized. Okay? It just makes life so much easier. Trust me.